Welcome everyone. In this presentation, I'll be talking about an adaptive observer strategy for unknown state and parameter estimation in polymer electrolyte membrane fuel cells. The authors of this work are affiliated to IRI and UPC. The general outline of this presentation will be the following. First, the technology of fuel cells will be introduced, and the necessity of adaptive observers will be presented. Second, the adaptive observer problem will be formalized. After that, it will be shown that standard nonlinear adaptive observer techniques cannot be applied in the concerned fuel cell problem, due to a relative degree limitation. For this reason, a novel adaptive observer scheme will be presented to circumvent this matching condition. This observer will be validated in a numerical simulation. Recent years have established the limitations of the current energy generation system. First, multiple sources point out to a decline of available oil reserves. Second, as the life conditions of developing countries are continuously improving, we can expect an increase of energy demand. Finally, in order to stop the climate change tendency, it is crucial to reduce the consumption of fossil fuels and increase the energy production of alternative green sources. In this context, hydrogen has attracted the attention of both the academy and the industry. This element can potentially be generated with zero carbon emissions and can be applied in a variety of contexts without generating any particulates or nitrogen oxides. For this reason, the demand and production of pure hydrogen has been increasing up to this day. Furthermore, if we look at the recent policies supporting the deployment of hydrogen, it can be seen that the general interest is towards transport applications. In this context, the most used hydrogen-based source of energy is the polymer electrolyte membrane fuel cell, which is the focus of this presentation. A fuel cell is an electrochemical device that converts the chemical energy stored in hydrogen into electricity through chemical reactions. Polymer electrolyte membrane fuel cells consist of a solid polymer that is used as an electrolyte between the anode and the cathode. These devices are characterized by its high power density, low operating temperature and zero carbon emission, which makes it an attractive source of energy for transport applications. The operation of a polymer electrolyte membrane fuel cell can be summarized as follows. The fuel cell's anode is constantly delivered with pure hydrogen. This hydrogen is processed at a platinum-based catalyst layer, which separates the element into protons and electrons. The protons travel to the cathode catalyst layer through the membrane. However, due to the membrane ionic properties, the electrons are forced to travel through an external circuit, which generates the electrical load of the device. In parallel, the cathode is fed with pure oxygen or air, which flows to the cathode catalyst layer, where the oxygen is combined with the protons to generate water and heat. The water generated in this reduction reaction is not just a sub-product that needs to be evacuated, but a crucial element for efficient fuel cell operation. If too much water gets accumulated in the fuel cell, one can expect unstable output voltage and performance degradation due to increased energy losses. However, if the electrolyte membrane is completely dry, increased ohmic losses are induced and the degradation of the system is significantly accelerated. As a consequence, the interest in developing active control algorithms for water management has increased in recent years. Developing water control algorithms poses a set of problems. First, available humidity sensors are slow, inaccurate, expensive and intrusive. Second, fuel cells are related to highly nonlinear processes and control-oriented models present significant uncertainty. This work proposes solving both problems through the design of an adaptive observer. The main objective of the observer will be to accurately estimate the liquid water saturation in the fuel cell, despite the presence of parametric uncertainty. Furthermore, the observer will include a parameter adaptive law that will also estimate the parametric uncertainty. To better understand the problem, the considered fuel cell model will be presented. The model depicts the fuel cell's thermal and water dynamics through an order 2 nonlinear system. The states are the stack temperature and the liquid water saturation in the cathode's catalyst layer. The controllable inputs are the exchange current and the cathode air velocity. The nonlinear functions fd, fp and v are known. Furthermore, it is assumed that the temperature can be measured, but the liquid-water saturation cannot. Additionally, there exist multiple techniques to measure the parameters K1, K2, K3 and K4. However, there is no reliable method to measure the parameters Ks and Kdiff. The objective of the adaptive observer will be to generate an estimation of the liquid-water saturation S, and the unknown parameters related to the water dynamics Ks and Kdiff. Let's formalize the considered problem. Assume that the nonlinear system dynamics can be expressed in the following form, where x are the unknown states, u are the controllable inputs and theta are a set of constant unknown parameters. The functions f, g and phi are assumed to be known nonlinear Lipschitz functions. Furthermore, the linear part of the system is assumed to be observable. Finally, it is assumed that the system is relative degree 1 from the measured output to the unknown parameters, which is depicted through this matching condition. As it will be shown, this matching condition is very restrictive, and developing a method to circumvent it will be crucial for the fuel cell application. For now, let's assume that the matching condition is satisfied. The objective is to generate an estimation of the unknown states and parameters of the nonlinear system, based on the measurement of the inputs and the outputs. This is not a new problem, and there are several standard adaptive observer techniques that can be implemented. A common nonlinear adaptive observer is the following one. Consider the next system, which is formed by a copy of the concerned uncertain model, a linear output injection term and a gradient descent-like parameter adaptation. Furthermore, assume that the observer design parameters satisfy the following matrix inequality. Then, the states x hat and theta hat converges asymptotically to the true values of the unknown states and parameters, respectively, provided that the vector b phi is persistently excited. This persistence of excitation condition roughly means that the input signal is rich enough, so the modes of the system related to the unknown parameters are excited, which can be checked through the next computation. One of the conflicts in this classic nonlinear adaptive observer strategy is that it is restricted to systems with relative degree 1 between the output and the unknown parameters, which is referred as the matching condition. This condition, in general, is very restrictive, and the considered fuel cell system does not satisfy it. For this reason, it is necessary to develop some strategy in order to circumvent the relative degree limitation. This work proposes relaxing the matching condition by means of applying an auxiliary signal. This signal z is designed so it is linear in the unknown states, relative degree 1 to the unknown parameters and rank observable relative to the matrix A. Then, independently of the system relative degree, the standard nonlinear adaptive observer can be applied if this auxiliary signal is taken as the measured output. Specifically, the modified adaptive observer takes the following form. However, the auxiliary signal will be unknown as it depends on the unknown states. Therefore, it cannot be directly implemented. For this reason, this work proposes achieving a robust estimation of the signal through a high-gain observer, which will be connected in cascade to the modified adaptive observer. In order to introduce the advantages and disadvantages of this strategy, next slides will focus on implementing this high-gain-based adaptive observer to the considered fuel cell model. Remember that the presented adaptive observer strategy is restricted to nonlinear systems with the following structure. This slide shows how the considered fuel cell model presents the adequate form and can be parameterized accordingly. Notice that the product of the vector b and the vector c is 0. Therefore, the system does not satisfy the matching condition. However, by following the auxiliary signal design insights presented before, it is possible to see that the sum of the stack temperature and the liquid water saturation is an adequate auxiliary signal, for the modified adaptive observer. Nevertheless, notice that the liquid water saturation is unknown. Thus, the proposed signal cannot be directly implemented. However, next slide will show how this auxiliary signal can be robustly estimated through a high-gain observer. The high-gain observer design will follow a standard procedure. First, it can be shown that the concerned system is uniformly observable in the cathode air velocity and strong differential observable of order 2. Furthermore, the model is a fine and relative degree 2 to the unknown parameters. Taking into account this observability analysis, it is possible to show that the following map is a diffeomorphism between the fuel cell model and a strict feedback form, in which a standard high-gain observer can be implemented. Specifically, a high-gain observer is a copy of the concerned fuel cell model plus an output injection term multiplied by the inverse of the Jacobian of the proposed map. The design parameters of the observer are bar ks, bar k diff, alpha 1, alpha 2 and epsilon. Bar ks and bar k diff are nominal values of the unknown parameters. These parameters can be used to introduce some prior knowledge of the parameters to the adaptive observer. Nevertheless, in the absence of prior knowledge, these nominal values can be fixed to 0. The tuning process of alpha 1, alpha 2 and epsilon can be summarized in the following theorem. If alpha 1 and alpha 2 are designed such that the following polynomial has all the roots on the left half-plane, then, the high-gain observer estimation error will converge to a bounded region, provided the design parameter epsilon is small enough. The estimation's error ultimate bound will be proportional to epsilon. Therefore, it can be made arbitrarily small by reducing it. Now, the robust state estimation of the high-gain observer can be used to estimate the proposed auxiliary signal Z. And the adaptive observer can be implemented as follows. The adaptive observer design parameters are tuned by using the matrix inequalities of the standard nonlinear adaptive observer. Consider the high-gain-based adaptive observer and assume that the high-gain observer is designed as presented before. Then, if the vector b phi is persistently excited, the state and parameter estimation error of the adaptive observer will converge to a bounded region. Furthermore, this ultimate bound can be arbitrarily reduced by decreasing the high-gain observer's design parameter epsilon. The claims of this work and the proposed high-gain-based adaptive observer have been validated through a numerical simulation. The constants alpha 1 and alpha 2 and the vectors L and M have been designed following the tuning process presented before. The learning rate gamma has been fixed to 1. Furthermore, it is assumed that there is no prior knowledge of the design parameters, thus, the nominal values bar ks and bar k diff have been fixed to 0. In this figure it is depicted the true evolution of the fuel cell liquid water saturation in blue and the estimation of two high-gain-based adaptive observer with two different design parameter epsilon. As it can be seen, both observers converge to a bounded estimation error, but, the ultimate bound is reduced in the case of lower epsilon. A similar result is obtained for the estimation of the first unknown parameter. Notice that, during the transient, the observer with lower epsilon presents the largest error. This is due to the increase of the peaking phenomena in the high-gain observer. Nevertheless, after the transient, the observer with lower epsilon presents the lowest estimation error. The same conclusions can be drawn for the estimation of the second unknown parameter. As a conclusion, this work has presented an adaptive observer for the estimation of PEM fuel cells water dynamics unknown states and parameters. It has been shown that the considered fuel cell model does not present the relative degree condition required in common adaptive observer techniques, and a modified strategy based on a high-gain observer has been proposed. The results of the observer have been validated through a numerical simulation. I would like to thank everyone for attending this presentation.